So we now have a process for working out the power series expansion of a function. In other words, the Taylor series of a function. We just need to know the nth derivative for all values of n, and we can put them all together into that form using Taylor series. Now, let's just list some of the important Taylor series. In these cases, they're centered at 0, so we're calling them Maclaurin series. Let's look at all of these important series representations for functions that we've been dealing with. Now the first one, this one we've known for quite a while. This is really just the geometric series on the right and its closed form expression for the sum on the left. However, in this context, we're kind of looking at it slightly different. We're saying, suppose I have this function 1 over 1 minus x. Do I have a series representation for it? Yes, it's the sum of x to the n where n goes from 0 to infinity. So that's its power series representation. Now, when you look at it that way, it starts to shed some light on some of the discussions we've just had. So, for example, here's our function 1 over 1 minus x. Its domain consists of all real numbers except 1. 1 is the only value I can't plug into here. Yet, when I look at the equality between these two things, the equality is restricted to a much smaller interval than the domain of the function. For example, 2 is in the domain of this function, but 2 is not a value for which the series converges. I can plug 2 into the series is written out here in full, and I see that I get 1 plus 2 plus 4 plus 8. That's a divergent series. So the equality doesn't hold on the entire domain of the function. It holds on some restricted interval. That's what we've listed over here. So we have to be careful. When we take a function and we construct its power series expansion, its Taylor series, we still have to worry about where that convergence happens. Where does the series actually represent the function? Where does the series converge? And does it converge to the values of the function? And so here I've listed not only the representations, but also the intervals on which you get the equality here. For the exponential function, we get that the power series expansion converges to the exponential function for all values of x. Same with sine and cosine. The one we worked out for cosine is here, and you get equality for all x values. Again, interesting to note that cosine is an even function. Only even powers of x survived in its expansion. Sine is an odd function. Only odd powers of x survive in its expansion. In some sense, you can think of this as being where the terms even and odd come from. A function is odd if only the odd terms are present in the Taylor series expansion. Okay, what about the last one? Arctan. You can work out its power series expansion, start taking derivatives, or the way we did it was we worked with the geometric series and changed the x to a negative x squared, got the series expansion for that, and then integrated term by term. That's how we got our arctan one. But nonetheless, we have our arctan expansion here, and it is valid only on the interval from -1 to 1. So what we're going to do is we're going to go ahead and use these to construct series expansions for other functions. So the important thing to note here is that we're asked to find Maclaurin series for these functions. We could go through the entire process of taking the derivatives, trying to find a pattern. So we take first derivative, second derivative, third derivative, evaluate at 0 and see if we can spot a pattern, and then try to put that all together into the form of the Taylor series centered at 0 and see if we can come up with a series that way. But that's an awful lot of work to do these particular examples because we've essentially done a lot of the heavy lifting already. So let's have a look at the first one. X squared e to the negative 3x. The point here is that we already know a series expansion for that. So recall e to the x has the expansion n equals 0 to infinity x to the n over n factorial. And this is true for x in the interval negative infinity to infinity, so for all real numbers. So that means that I can just replace x with this expression, e to the negative 3x. So I'll put negative 3x in for x, and I do the same thing in the series. So that's negative 3 x to the n over n factorial, which I could write as negative 3 to the n x to the n over n factorial. Now, my original function that I'm interested in, which is x squared times e to the negative 3x, well, I have an expansion for e to the negative 3x already done. So that's negative 3 to the n, x to the n, all over n factorial. And now I can multiply the x squared in term by term. And I get that this is negative 3 to the n, x to the n plus 2, all over n factorial. And what interval does this equality hold for? Well, the original expansion for e to the x held for all real numbers. So does this one. And there's our result. Notice knowing the expansion for e to the x allowed us to get the expansion for x squared e to the negative 3x rather quickly, rather than having to do all these higher derivatives and trying to spot patterns for the coefficients. We got this immediately from the series expansion for e to the x. So how about the next one, sine of x squared? So we recall again that we know sine of x. Sine of x is the sum from n equals 0 to infinity, x to the 2n plus 1 all over 2n plus 1 factorial, negative 1 to the n. So that's our sine of x. It's exactly what was written here. Okay, and it is worth knowing this one. Know this one. Exactly as I did on the last page, be able to write it down. Notice how I started to write it down. I started with the x to the 2n plus 1. Sine is an odd function. I started with the fact then that only the odd powers of x survived. They're matched by the 2n plus 1 factorial on the bottom. The power matches the corresponding factorial on the bottom. And they alternate, so there's negative 1 to the n. So it's absolutely worth remembering that one. So what does this mean? Well, this is true for x in negative infinity to infinity. I'm interested in not this, but sine of x squared. So now this becomes the sum from n equals 0 to infinity, negative 1 to the n. And now I pop x squared in for x to n plus 1 factorial. And I can rewrite the powers of x in this way. So that's a negative 1 to the n, x to the 4n plus 2 all over 2n plus 1 factorial. And so there is our series expansion for sine of x squared. You can do quick mental checks too. You can say, well, sine of x squared, that's got to be an even function now. So I look over here at the series representation, and the power of x is an even number. So, you know, quick checks just to see, did you make any mistakes? Does it seem plausible that this should be the series representation of that? What's the last one? X over 9 minus x squared. So C. X over 9 minus x squared. How do we get this one? Well, I notice that if I factor out an x and I factor out a 9, then I can write what's left as a 1 minus x squared over 9. And this, I know the series expansion for this, because this is the sum of a geometric series. So this is the sum, n equals 0 to infinity, of x squared over 9 to the power of n. So this is x over 9, sum, n equals 0 to infinity, of x to the 2n over 9 is 3 squared, so I could write that as 3 to the 2n if I wanted. Now I can multiply x over 9 in, and I get x to the 2n plus 1 over 3 to the 2n plus 2. And so there is our expansion for x over 9 minus x squared. Where is it valid? Where is this valid? Notice that just writing this doesn't indicate for what x values do I have the equality. So when I do this, I sort of have to backtrack up here and say, well, where were these things valid? The first expansion was done here, 1 over 1 minus x squared over 9. I used the fact that it was a geometric series. So let's flip back here. This is the one I'm using this one here. 1 over 1 minus x is the sum of this thing when x is in magnitude smaller than 1, when x is between negative 1 and 1. So this is true when x squared over 9 in magnitude is smaller than 1. Or another way to say that is when x is smaller than 3 in magnitude. So this is when x is smaller than 3. So our power series representation, our Maclaurin series for this function is this on the interval between negative 3 and 3. So I just want to have a brief look at the table of series that we have so far. These are really important ones that you should know, and there's in fact one more that I think is worthwhile adding to the list. It's one that we've worked out already, the logarithm of 1 plus x, and that's equal to sum as n goes from 1 to infinity, negative 1 to the n plus 1, x to the n over n. Now where did we have equality here? Do you remember? X between what and what? Well, think about where this came from. We derived this by starting with the geometric series and taking x to be, or plugging in negative x for x. So that became a 1 plus x, and this became a negative 1 to the n, x to the n, as n goes from 0 to infinity. And since this is a geometric series, we know that this works for x between negative 1 and 1. Now to get down to here, we integrated each side. Integral of 1 over 1 plus x is logarithm of absolute value of 1 plus x. The integral of this thing is the series we have on the right. So it means that if the original radius of convergence is 1, then the radius of convergence for this series must also be 1. But we still need to figure out what's going on at the endpoints. Notice when we plug 1 in to this expression, I get the alternating harmonic series. And we know that converges by the alternating series test. So I can actually put an equality there. The series converges, and by continuity it converges to the logarithm of 1 plus x. What about the other endpoint, negative 1? Well, if I plug in negative 1 in here, then that just becomes the harmonic series, which diverges. So we don't have equality for the one side. We do have equality for the other side. And so what's interesting about this is that we now know then that the alternating harmonic series, n equals 1 to infinity, so which is, work out the values here. This is 1 minus 1/2 plus 1/3 minus 1/4, ... That alternating harmonic series converges to the logarithm of 1 plus x. So that's pretty neat. We knew the alternating harmonic series converges, we just didn't know what it converged to. Now through studying this function, the logarithm of 1 plus x, we see that the alternating harmonic series comes about by evaluating the representation for the logarithm of 1 plus x at 1. So it must converge to log of 2.